Hi and welcome to part 2 of my video playlist about the best methods to olefinate ketones. This presentation is about the use of metallated sulfones and silanes as carbon nucleophiles. These reagents have been used less often than phosphorus ylides, but are potentially valuable alternatives. For instance, if a certain stereo or chemoselectivity cannot be attained with Wittig reagents. Alkyl sulfones are slightly acidic and can be metallated by strong bases and then added to ketones. The resulting hydroxyethyl sulfones are usually stable or eliminate water to yield alpha-beta unsaturated sulfones. These can be reduced to alkenes by cleaving the carbon-sulfur bond, for instance with sodium. Electron-deficient aryl alkyl sulfones, however, can yield alkenes directly upon reaction with aldehydes or ketones, as shown here. If the sulfur-bound aryl group is sufficiently electron-poor, the initially formed alkoxide can undergo intramolecular aromatic nucleophilic substitution of sulfinate and then fragment into an alkene, a hydroxyarine, and sulfur dioxide. Most reported examples are olefinations with benzothiazolyl sulfones, but pyridyl, pyrimidinil, nitrophenyl, bis, trifluoromethylphenyl, and tetrazolyl sulfones can also be used. In order for this reaction to proceed smoothly, the arene must be sufficiently electron withdrawing to undergo aromatic nucleophilic substitutions readily. Accordingly, the resulting phenoxide will not be very basic and will not necessarily react with the liberated sulfur dioxide. Thus, sulfur dioxide will neutralize one equivalent of base, and two equivalents of base are usually required for this olefination to proceed to completion. Occasionally, though, good results can be obtained with only one equivalent of base. Sulfones are 4 to 7 orders of magnitude less acidic than ketones and usually require strong bases to undergo condensation reactions. Silanes are still less acidic, but as shown by the two compounds in the second row of this slide, silyl groups do enhance the acidity of alkyl groups slightly if compared to methyl or terz-butyl groups. This example shows that metallated sulfones are powerful nucleophiles that can olefinate ketones already at low temperature. Although acetophenone is probably more acidic than the sulfone, this olefination succeeded upon adding the base to a mixture of ketone and sulfone. Almost two equivalents of base were needed, though. The stereoselectivity could in this case be influenced by the substituent at the tetrazole ring. Ketones are not usually olefinated with high cis-trans selectivity, but in this instance mostly the cis-alkene was formed. Here, a structurally more elaborate enolizable ketone had to be methylated. Again, addition of the base to a mixture of ketone and sulfone at low temperature gave a high yield of the target alkene. The use of a lithium base probably helped to prevent elimination of hydrogen chloride by the tertiary alkoxide. A more dissociated sodium or potassium alkoxide may have eliminated chloride faster than the highly associated lithium alkoxide. Even enol ethers can be prepared from ketones with the aid of alpha-oxysulfones, as shown here. The corresponding phosphonium salts also react this way. Also, alkoxides can be used as base for this reaction. Again, despite tetralone being an enolizable ketone, addition of an excess of base to the mixture of ketone and sulfone brought about the methylation. The olefination of aldehydes or ketones with silanes, the so-called Peterson olefination, is assumed to proceed either by an almost concerted 2+2 cycloaddition, like the Wittig reaction, or by intermediate formation of a deprotonated beta-hydroxysilane. Again, the precise mechanism will probably depend on the electronic and steric properties of all the reactants. Like phosphonium salts, some silanes can also be deprotonated directly by treatment with organolithium compounds, as in this example. Reaction of the lithiated silane with a benzophenone yielded a substituted tetraphenylethylene. Also, enolizable ketones can be olefinated with lithiated silanes, as shown here. In this case, the ketone contained a good leaving group in beta position, but no elimination occurred. 2 and 4 methylpyridines are acidic enough and can often be condensed directly with aldehydes or ketones, sometimes even under acidic conditions. Therefore, an additional activation by phosphorus, sulfur, or silicon is not always required. Acetaldehyde can only rarely be used as carbon nucleophile directly. It is too acidic and its enolate therefore too unreactive. Moreover, acetaldehyde quickly oligomerizes upon treatment with bases. Useful synthetic equivalents of acetaldehyde are imines, as the one of this example. After lithiation with LDA, it was used to olefinate the sterically crowded terpene phenchone. The fair yield was, however, not only caused by the low reactivity of phenchone, but also by the use of only equimolar amounts of nucleophile. It is always a better strategy to use a slight excess, say 10 to 20% of the least expensive reagents, to drive conversion of the most precious starting material to completion. In this example, an enolizable ketone with a center of asymmetry in alpha position was olefinated with silylated methyl acetate. The yield was high, but as is often the case in ketone olefinations, a mixture of cis and trans isomers resulted. In this instance, a better result could be achieved with the corresponding phosphonoacetate. Sodium hydride was used as base, and mostly the trans isomer was obtained. Let's now check out some potential side reactions. During olefinations with metallated alkyl sulfones, one occasional side reaction is the formation of symmetric alkenes from the sulfone. Here, for instance, 17% of a symmetric stilbene was obtained as byproduct. These alkenes are probably formed by SN2 displacement of sulfinate, as shown in the lower equation. Then, if hydroxide, alkoxides, or other nucleophilic bases are used, the aryl sulfone may undergo an intermolecular nucleophilic aromatic substitution, as shown here. In this second example, it was not the base, but the ketone enolate which acted as nucleophile to displace sulfinate. Such side reactions may be prevented by metallating the sulfone with a non-nucleophilic base, such as LDA, at low temperature and then adding the ketone, again at low temperature. Treatment of ketones with sulfones and bases can also bring about the formation of dienes, as shown here. These are formed when a condensation of the ketone with the sulfone occurs first. Isomerization of the intermediate vinyl sulfone into an allyl sulfone, followed by elimination of sulfinate, then yields the observed diene. This side reaction should not occur with strongly electron-deficient aryl sulfones, because these should not form condensation products but undergo intramolecular aromatic nucleophilic substitution. Then, not all condensation products must undergo isomerization and sulfinate elimination, as on the previous slide. Alcohols or condensation products may also be sufficiently stable to be isolated. In this example, depending on the workup conditions, either an olefination product or a condensation product was obtained. Ketones with leaving groups in beta position can be converted into enones by even weak bases. The olefination of such ketones is therefore difficult, and enones are frequent byproducts, as in this example. Enones can also act as Michael acceptors, what may complicate olefination attempts. In this instance, a silylated acetate enolate underwent both olefination and Michael addition upon reaction with chalcone. Moreover, a partial reduction of the ketone to an alcohol occurred. Strongly acidic or highly enolized ketones may also just protonate a metallated sulfone or silane, and this can be difficult to prevent for a given pair of reactants. The best strategy is to metallate the sulfone or silane stoichiometrically with a strong base in an apolar aprotic solvent and then add the ketone slowly at low temperature. Then bases can always promote aldol addition and condensation reactions. Although alkyl silanes show only a weak partial negative charge at carbon, treatment with very acidic ketones or protic solvents can cause protonolysis and cleavage of the carbon-silicon bond. The reaction of metallated sulfones or silanes with ketones can sometimes yield stable tertiary alcohols. Olefin formation may either be carried out in a second step or be accelerated by addition of chlorotrimethylsilane or boron trifluoride etherate. Here are some more examples with various bases. You can also find this reference list in the description of this video. Mostly strong bases are required for these olefinations. The next presentation is about condensations of ketones with aldehydes, other ketones, carboxylic acid derivatives, and some further carbon nucleophiles. These condensations are by far the most relevant ketone olefination reactions, but do not always enable a good control of the cis-trans selectivity. So long.